All right, let's go ahead and get this underway. Maybe underway. We'll see what happens here. All right. So we're going to be dealing with caches. And this is specifically the for loop problem. I'm going to use the for loop that is within our be question 11 through 13. It specifically is referencing a three-dimensional for loop and defined by n, where we have arrays A, B, C that are n by n. Now, for these kinds of questions, you can be asked two types of questions. You can be asked first to find compulsory misses. And then the second type is just regular misses. Now for the compulsory misses, we can use a nice little formula. That's just n, which is the dimension that defines the array, divided by the element division. And then we want to make sure we also raise that n to the power of whatever the dimension size is. And then that's how we find a compulsory, how many compulsory misses for one array. Now, if this is for one, for many of them, it's just the sum of this. So it'd be the sum of the compulsory misses for each array. Now, how does this look? So given A, which, if I remember, A was defined as n by n, which means it's two-dimensional. And then for the element division, we need to figure out how many blocks are we dealing with. So it says the cache is configured with a block size of 4 by 8. Our cache block size of 4 by 8 are 32 bytes. So we have 32 bytes for our cache block size. And we also want to fit in a bunch of integers. So we need to see how many integers we can fit in each block. So we're going to divide that by 4 bytes. And this is also one word. So we find that we can only fit 8 elements, which means that if we have a block that looks like that, or a block table that looks like this, or not block table, but just series of blocks. So we have block 0, 1, 2, 3, and so on. That means block 0 can only fit 8 elements. Block 1 can only fit 8 elements, and so on. Which means that we're based on that, which means we're looking for unique misses. Not anything that's going over the same thing. So compulsory misses are unique misses, or anything that was accessed that hasn't been accessed before and is just unique to that iteration, or to all the iterations at once. So we can calculate that for each array, and we figure out how many unique misses are in each array. So we would do this for A, B, and C being all two-dimensional arrays. We would do the n, which we know was, we can define as whatever we want. So we can put in, say, n equals 8. We'll say n to the 2 divided by 8 plus n to the 2 divided by 8 plus n to the 2 divided by 8. This comes out to 3 times 24, or sorry, 3 times b 8 squared, 64 divided by 8, which is 8. And that's 24. Okay. Now, second question, which for this one, we're going to be given usually the size of the cache, the size of the cache, of course, the for loop that we were given. So for this one, I'm going to use the for loop that's given in the code. Do for I equals 0, I less than n, I plus plus, for j equals 0, j is less than n, j plus plus. And then for k equals 0, k less than n, k plus plus. And then I'm just going to do this in a Python way. I just have colons. But you get it. It's a nested for loop. And the equation that it uses is C I J equals AIK plus BJK. Now looking at this, we can tell, well, you know, we can go ahead and try to run through it and be like, well, there's misses here. There's probably going to be at least 2 misses each time it's around, which is can work. The problem is we start running into is how are these actually laid out in cache. So if we remember, we are dealing with a should be a 2-dimensional array. The 2-dimensional array is 256 bytes of memory. Let me just verify that real quick. Yeah, so we're going to deal with, it doesn't look like one is set. So we set associative. Yeah, all right, it doesn't matter. I'm going to go ahead and use 256 bytes for the cache size. So go ahead and do that. So cache size equals 256. Oops, not 56, 256. This is in bytes, so 256 bytes. And okay, so for 256 bytes, we're going to go ahead and say, well, we want to calculate first off, how does this look as far as our tag? You know, we always want to calculate the set. God, I can't think today. Set ID, offset, and for this, tag isn't really a issue, but we can still calculate that. So to calculate our set ID, we're just going to do log base 2 of the cache size multiplied by the cache block size, which is 32, and then the associativity, which we're going to set to 2. And then this is going to give us 2 to the 2 log 2 to the 2, or aka just 2 bits for our set. And for our offset, it's just going to be as simple as taking the log of our cache block size, which is 32, equals 5 bits. And then if we do the math on this, subtracting from 32, we get this one as 25 bits. Now that we have this, we also want to lay out how our cache accessing looks. So what I mean by that is if we have A, 0, 0, what is defined, where is this at? Which block is this at? So since we know that there's supposed to be 8 elements in each block, 8 elements would be looking like A, 0, 7. And it would look like this all the way to the last one, which would be A, 7, 0, A, 7, 7. Now this is if the cache is of size n equals 8, because it'd be an 8 by 8 array. And where this is going to be block A1, and this would be all the way to block A 8, not A7. So A1 to A8. And it's going to be the same kind of concept. You have B1, B8, C1, C8, and so on. Now, how these are laid out are going to be in what's called memory and row. It's going to be memory row major format. This is what actually Mahesh said is going to be similar to like on the final, which we did see before. This just means that when we're trying to pair these blocks with their respective set ID bits, we're just going to do it one after the other. So A is going to be next, A1 is next, going to be next to A2, A3 is going to be next to A4, and so on. So it looks something like this. So we have our set bits, and we do A1, A2, A3, A4, A5, A6, A7, A8, B1, not A, B1, B5, B2, B6, B3, B7, B4, B8, and C1, C5, C2, C6, C3, C7, C4, C8. So this is going to be how our accessing looks. So every time we try to access A1, it's going to be under the guise of tag 00. This is important when we start caching because then we need to figure out if it's a hit or a miss. So if it hits that correct set ID, then, well, that will define what happens. We can see that now. So when we go through the execution, let's go ahead and build our table real quick. So we have 00, 0, 1, 1, 0, 1, 1. And that's them as two-way set associative. So I'm going to actually move this table over down here because we're going to use it to reference things. So for iteration 1, we have not I1, I equals 0, j equals 0, k equals 0. And we're going to access. So we're going to go right to left. And let's go ahead and grab this equation. And then we'll go ahead and bring it down here. Okay. So right there. All right. So if we're accessing right to left, we're going to be dealing with first B, J, K. So B, 0, 0, A, 0, 0, and C, 0, 0. And referencing our table over here, we notice that all those are in tag 0, 0. So put in B0, that's a miss. Actually, let me make sure. So B1, A1, C1. Let's put in B1, that's a miss. And I'm going to tally them up here. Put in an A1, that's a miss. We also don't evict anything yet. So I'm going in a FIFO manner too. So just making sure. So there's 3 different replacement policies that could be there. There's FIFO, first in, first out, last recently used, and most recently used. So the last thing that was put in basically would get evicted. The first one to get put in out of everything would be evicted. So this is going to be the oldest item. And then FIFO is going to be the first thing that goes in, is the first thing that goes out. So it's kind of closer to LRU. But I'm going to use FIFO for this example. So then in this case, put in C1. Well, B1 is going to be evicted first. So go ahead, that's a miss still. But that's how the cache looks for now. Now we're going to do iter 2. I equals 0, I equals j, k. Oh, no, this is completely wrong. j equals 0, and k equals 1. And then our access, and the block, we're going to access b 0, 0, or sorry, 0, 1, because jk. Then ik, we're going to access a 0, 1, and then c, ij, so it's still c 0, 0. So these blocks are still in b1, a1, c1. Now, this is where we can start trying to develop patterns here. So b1 is obviously a miss. So we're going to evict a1 and put b1, put another tally. Then we're going to do a1, evict c1, put a1, and then we need c1, so we evict b1, put in c1. So just looking at how this is set up, we notice that k is always going to change here. A is always going to change because k is also in that. And k goes all the way from 0 to n, which in this case is 8. So it's going to go 7 iterations. Now, c is going to be constantly the same. And then on the 9th iteration, it's going to change. It's going to be the only time it changes. But for that time being, that means that A and B are going to be always hitting on, are going to be always trying to access set ID 0, 0. Because if you notice, A1 and B1 are there. And if we recall, A1 is A0, 0 to A0, 7. And then B is likewise. So yeah, we're not going to be going anywhere past A0 and B0 for accessing the sub-elements. So that means that we're going to be constantly missing, especially because now we have to deal with the C, which is going to be also hitting in set ID 0, 0. So we can chalk it up to every single access is a miss. And if we look at how the state looks currently, we have C1 and A1 still there. We'll do it for one more iteration, see what it looks like. Do I equals 0, j equals 0, k equals 2. So now we're accessing B0, 2, bless you, A0, 2, and then we're going to be accessing C0, 0. So this is B0, or sorry, B1, A1, C1. So we evict A1 for B1. We evict C1 for A1. And we evict B1 for C1. It's almost like they swapped. So this is going to keep going around for each iteration. And if you were following along, we totaled up 3 more misses. So we can say, we're at iteration 3, so I equals 2. So, or k equals 2 would be, so once it gets to 7, which this means that we have 5 more iterations left, we can then just do some quick maths and say there's going to be a total of 15 more misses happening, and just tack that onto what we have. So currently we have 5, 6, 7, 8, 9. 24, right? Yeah. So 24 misses currently. And then on the 9th iteration, if we want to check it for the 9th iteration, we'll go ahead and actually have, I'm going to iter 9 equals 0, j equals 1, k equals 0. So we'll be accessing B1, and then 0. A, 0, 0, and C, 0, 1. So as we probably assumed, this will be the only hit because we're still in the cache block 0, or A1, I should say. So the other ones, though, 1, 0, that's now in B2 for the catch block. A is, well, how we started before, 0, 0. So we're still in, where this one is an A1 still. And then, as before, too, as with B2, we're actually going to increase on C. So now this is going to be C0, 1. So this is still going to be in C1. So we don't have to worry too much about B2 actually getting in the way. So we have a hit right here and a hit right here. And then we just have to add B2. So we actually have one miss. I was wrong on that. So we add plus 1 equals 25 misses, which this should be pretty much all we would need to do for this. And I can also explain further if need be. So let me know. Thank you for watching.